Guys, let's look at this problem right here. Here we have a very long wire carrying current I is bent into the shape. The question here is, what is the magnetic field at the center of this 3/4 of the circle? Now to find this one out, it's very hard to solve this one altogether because we have a bent shape, not a regular shape, right? So what we can do is we can divide this one into three parts. Like we can take this line path as 1, and we can take this 3/4 of the circle as 2, and then we can take the top straight long wire as 3. Okay, then we are going to solve these three individually. Now let's take this first part. If you take the first part, this is going to be just the line, and here we can use the Biot Savart law. Biot Savart law says that dB, the small segment of this current, small segment of the magnetic field caused by this current wire, is equivalent to mu naught I dl cross point vector r divided by 4 pi r square. Okay, this is the equation. Now here we have, now let's look at this one, dl cross r point vector, and dl is going along this direction, right, along the wire's path, but this point vector is pointing toward the center of this one. And if you look at it, this is going in this direction. Let's use a different color. This dl is going in this direction, and this r point vector is in the opposite direction toward the center of this 3/4 of the circle. So this is in the opposite direction, and this is exactly along the path. Like if you look at this one, this is 180 degree, right? So instead of dl cross r, we can write dl, magnitude of dl, sine theta. Both of them are same thing. And if we put theta, here we're going to have sine 180 degree. And we know that sine 180 is equal to 0. Therefore, the whole thing is going to be 0 because we are going to multiply everything by 0. So this one is 0. Let's notice this one 1. This is at 1. Okay. So at 1, we are going to have magnetic field dB is equal to 0. Therefore, B is equal to 0. Okay, so this is at 1. Now let's go to the 2. At 2, we are going to have a 3/4 of the circle. Again, we can use the Biot Savart law. That's dB is equal to mu naught I dl and cross point vector r over 4 pi r square. Okay, now let's look at this one. Here we have the current going in the direction along the circle. So this is the dl is traveling in a circular path, and if you look at the r for each of the segment is going toward the center, right? For each of them, if you take the segment, it's always 90 degree, or these two are 90 degree to each other, right? So the sine angle, if we replace this dl cross r with dl sine theta, we are going to have dl sine 90. So this is going to be just mu naught I dl over 4 pi r square, but here the radius is given by capital R, so we can just replace this small r with capital R square. Okay, so this is our dB, and to find B, what we have to do is we have to integrate this one. If we integrate dB, that's going to give us the total magnetic field. So this is going to become integral mu naught I dl over 4 pi r square. So from this equation you can see only the L value is changing, others are constant, right? Because we have dl right here, we don't have anything related to L in this one. So we can move all the others to the front. So mu naught I over 4 pi r square integral dl. Now limits of integration. If you look at this circular path, the current wire is going in a circular path, and this dl represents the length of the current that is going from 0 to 3/4 of this circle, and for length of the circle is given by the circumference, that is 2 pi r, and here we are going to have 3/4 of that one because we don't have the full circle. So 3/4 of the 2 pi r, 2 pi capital R, because we know the radius, that's capital R, and that is dl. We are integrating with respect to L, and here if we integrate dl, that's going to be just L, right? So we are going to have mu naught I over 4 pi r square, capital, I forgot to put capital R square, and then here we are going to have L, that is going from 0 to like a 3 over 4 to 5r. I can simplify this one, like 2 cancels, so we are going to have 3 over 2 times 5r. And if we replace this one, like if we plug this one, this is going to be just multiplication of 3 over 2 5r, and if we plug 0, the whole thing is going to be 0, so we don't have to put that one, right? We just have to write the first part, the upper limits of integration. So the answer is going to be b is equal to mu naught I 4 5r square times 3 over 4 times 2 5r, that's going to be just 3 over 2 5r. 3 over 2 times 5 times r. Here we can simplify this one furthermore. We have this 2 times 4, that's going to be 8. And finally we will end up with 3 over 8. And then this 5 cancels, and one of the r cancels. Let's show this one here. So this 5 and this 5 cancels, r square and this square cancels. So finally we end up with 3 over 8 mu naught I, that's it, mu naught I over r. We have r here, and that's our answer for this one. And we have to know the direction, so let's write everything in the same color. 3 over 8 mu naught I over r. And to look at the direction, you can see this is, if you point your thumb along this current direction and if you curl it, at the center you will see your, like, the curled finger comes outside of the screen. So the magnetic field here is going to be just outside. So we put a dot like this, that represents the outside of the page. So that's going to be the magnetic field at the segment 2. Now let's go to the segment 3. Segment 3, what we can do is, here we can use the Ampere's law. Ampere's law says, let's write the Ampere's law. Ampere's law that says line integral b dl is equal to mu naught I enclosed. Okay, enclosed. But this is true if this is a very long straight wire. But here what we have to do is, we have to imagine this like a very long straight wire. To do that, what we are going to do is, we are going to think like this wire goes like this all the way right here. And then if we draw this one, like, we have to think an imaginary circle. For Ampere loop, we have to think a imaginary Ampere loop is going to look like this. Let's draw that one here. Okay, we are going to have an imaginary Ampere loop. I draw a circle. Okay, so we are going to have an imaginary Ampere loop like this. And to show this one imaginary, what I'm going to do is, I'm going to put it a dot line. Okay, let me reduce this one. Okay, this is imaginary, so we put a dot line, so it represents it's imaginary. Okay, so this is our imaginary circle, and from this one, like, to look at the direction, you can point your thumb, and if you curl it, you will see this will be going in this direction, like this, right? This one should be okay. So this is our imaginary Ampere loop, and from this one we are going to find, using this one, we are going to find the magnetic field through this long straight wire. Okay, now let's go ahead and do that. Here we have integral b dl, and you can see this b is a constant because by symmetry you can see the magnetic field is not going to change. So we can say this is b outside, and this is going to be integral dl. And for this imaginary circle, the length is going from 0 to the circumference of this imaginary line. That is equivalent to 2 pi r. Okay, the radius is same as this, so 2 pi r. So we can say 2 pi r and dl, and then that's it for this one. That is equivalent to mu naught I enclosed. I enclosed, the current enclosed by this circle is this same I, right? So we can just write capital I right here. And let's do the integration. And if you integrate dl, that's going to be just L. So we are going to have B L, and this L is going from 0 to 2 pi r. That's equal to mu naught I. Let's write this one. Okay, let's leave it like this. Okay, this is going to be just B times 2 pi r. That's going to be equivalent to mu naught I. Therefore, B is going to be equivalent to mu naught I divided by 2 pi r. Okay, so this is the magnetic field, but this is true if we have a very long straight wire. But here we assume this is a very long straight wire, but actually it's half of it, because we think like this is at the center, so we are just having half of it. So what we have to do is we have to divide this one by 2 to get the real magnetic field. That's going to be just B is equal to mu naught I over 4 pi r. 4 pi r. Okay, so that's going to be the magnetic field at the segment 3. Now here, this one, to look at the direction, you can see that when you point your thumb along this current direction, at the center, this is going to come out, right? Your curled finger will come out of the page. So it means this is also coming out of the page. So we put a dot like this. Okay, so this is going to be the magnetic field right here. Now, using the superposition principle, we can combine all the magnetic field, the total magnetic field, BT, let's call this BT. BT is going to be just addition of B1 plus B2 and B3. Okay, B1 is equal to 0, so this is going to be just 0 right here, plus B2, this is B2, this is B3. B2 is equal to 3 over 8 mu naught I over R, and then B3 is equal to mu naught I over 4 pi r. Okay, now let's get rid of this 0, because we don't need this one. Let's get rid of this 0, and this is going to be our B total, right? This is our final answer. B total is equal to 3 over 8 mu naught I over R plus mu naught I over 4 pi r. Okay, and also you have to know the difference between dl. This dl right here, Ampere loop dl, and this Biot Savart law dl are totally different. For the Biot Savart law, we actually have a wire segment and we pick up a small segment, and that's our dl, right? But for the Ampere loop, this circle does not exist. So we just assume there's a circle existing, and this is just an imaginary dl, right? That's the difference. I hope this helps. Thanks for watching.